Okay, if you look at the whole page, I've got it twice, because I'm going to do it two ways. Okay, now some of you are going to look at this, and you're going to remember that I could write this thusly. And so there is an inside function of the cosecant 4x, but that's not the way we want to think of it. Don't think of it that way. That's not, I mean, it's not wrong, but it's not useful. You don't want to think about the cosecant squared in this manner, where you're kind of thinking, oh, it's cosecant and it happens to be squared. And I know I'm not explaining this particularly well. You want to think of cosecant squared as, oh my God, I do know the antiderivative of cosecant squared. Remember the idea of antiderivative indefinite integral. You're always asking yourself, what has a derivative of? What has a derivative of cosecant squared? Negative cotangent. So you really don't want to change the cosecant squared. You know the answer to cosecant squared. So this isn't a helpful way to think of the problem. So I'm not going to think of it that way. I'm going to white it out, because I do know the answer to cosecant squared, so I'm not going to mess with that. But the 4x, and the only reason I'm doing this twice, we actually have already talked about this sort of problem, and we'll do it the second way, the way we talked about it in the last section. But I'm going to do it with a u substitution to begin with, because if you're fond of apps, please don't be fond of apps. Apps do not help you learn the material. But you take a picture of that in Symbolab, and the way Symbolab is going to do it, they're going to do it in the most hard way possible, first of all. That's what a lot of apps do. They do things in the hardest way possible. It's going to do it in a hard way, and it just makes it harder than it has to be. And the same thing with view and example. View and example is going to do a u sub on it. And it's not wrong to do a u sub, it's just harder than it has to be. But I'll do it once with a u sub to show you, yes, we can do a u sub, but then we'll talk about what I hope you will do. So now, forgetting that I said all that, going back to not going to mess with the cosecant squared. I essentially know the answer to what is the antiderivative of cosecant squared. Asking myself, what has a derivative of? Well, what has a derivative of cosecant squared? Negative cotangent. So the cosecant squared isn't the issue. It's about that 4x. So I will let u equal, and that's still an inside function. It's inside the cosecant squared. And so u equal 4x. That's going to make du. Right. Be more specific. Choose u. Calculate du, and remember that's du derivative dx, and you're just looking at this little line right here, so du derivative 4x is 4 dx, and then 3 solve for dx. So dx equals du over 4, that you're just looking there and solving for dx. And I'm just going to write this so it's a little bit bigger. Then I make my substitution. That 4x is going to be u. Dx we calculated over here. Dx is going to be represented by du over 4. I get some canceling. The 4 and the 8 cancel, leaving 2. And so for step 4, I end up with 2 cosecant squared u du. And there's the point to a u substitution. I took something that was a little complicated looking. I've transformed it into something that's much easier looking in terms of one variable. So step 5, still unnecessary. We'll eventually get to it. So step 6, I integrate. That 2 just hangs out. Then I ask myself, what has a derivative of positive cosecant squared? And that's negative cotangent. And then back to the original variable, u was equal to 4x.
And so that's going to be negative 2 cotangent 4x plus c.
And there I did it with a u substitution, and of course you could check that by differentiation, and I will leave the checking up to you. And I did it that way because for those of you that are wedded to View an Example and your apps, that's the way they're going to do it. But these linear arguments are going to creep up so very often that we want to try to learn to use u substitution for more complicated things. Yes, we are able to do that. But what we talked about in the last section were things of this form, right here. Cosecant squared mx, that we talked about that last section, that when your angle, your argument was linear, and even if it's mx plus b, that the effect of that slope, the effect of the m when I'm integrating, when I'm doing anti-differentiation, will be that I will always just divide by that slope. Opposite of the chain rule. If I was differentiating, chain rule would have we multiply by that m. When I'm anti-differentiation, I'm going to divide by the m. And I really want to have you embody that idea that when I have a linear argument, mx plus b, now if this is mx squared, totally different issue. But when I have a linear argument and I'm integrating, the effect of that slope every time is that I'm going to divide by it. Because that's just the opposite of differentiation. Differentiation, the effect of that, chain rule, I'm going to multiply by the m. Integration, since it's the opposite, I'm going to divide by the m. So what I would really prefer here is that you remember that using that cosecant mx, the antiderivative of cosecant squared mx dx is negative 1 over m cotangent mx plus c. Just write the answer down. That's going to be negative 1/4 cotangent 4x plus c, or negative 2 cotangent 4x plus c. That when you have those linear arguments, mx plus b, the effect of that slope every single time is I'm going to divide by it. And so this is what I'm hoping to get out of all of you, that on these simpler cases, you'll just recognize what the effect of that slope is and you will divide by it. Okay, moving on. Next problem. And kind of foreshadowing, it's the problem after that. Got it twice. So we'll explain why it's twice in a minute. Okay, so let's rewrite this a little bit. That's 6 out in front. It's just a coefficient. I can take that out in front. And so that's tangent of 1/2 x to the 5th and secant 1/2 x squared dx. And so I look at it, and again, it's a product, it's a composition. I cannot easily simplify it. And so I got to decide what I want to do. Should I let u equal secant, or should I let u equal tangent? But remember, you want to see derivatives in the problem. Secant squared is a derivative. Secant squared is the derivative of tangent. I want to see derivatives. And so what I'm going to let here is I'm going to let u equal tangent of 1/2 x. Because then that's going to make du, differentiating the derivative of tangent, is secant squared. The angle doesn't change. Differentiating, chain rule, 1/2 dx. And notice this is in the problem. Is in the problem. So, is working. You want to see the derivative when you calculate du. You want to see at least the variable part of the problem in the variable part of du in the problem. Now, you don't necessarily need to see the whole thing. Back when we did this problem, we chose for u 3x squared plus 1. We calculated du, which is 6x dx, and we did have the x in the problem. And then we noted that up here. That, we noted that when I took the derivative of this, it would be 6x, and we did have the x in the problem. When you have the variable part in the problem, this will probably work. That 6 took care of itself. That when I solved for dx, that 6 just sort of took care of itself. It ended up in that denominator, and we just pulled it out. So I can be missing a coefficient, but I've got to have the variable part. And so this guy worked because when I calculated du, 6x dx, the x was in the problem. Same thing here. The variable part, secant squared 1/2 x, that's in the problem. 3. Solve for dx. And so dx is going to be 2 du divided by secant squared 1/2 x. My handwriting is not good today. Not that it's ever particularly good, but it's a little worse than usual today. So I'm just going to rewrite this again so I have a little more space. And I'm going to call this back to secant squared of 1/2 x dx, written that way. Then doing my substitution, the tangent 1/2 x dx is going to be du. Then dx is replaced by 2 du over secant squared 1/2 x. And we get the canceling. That 6 and the 2 can both come out to the front. Yes, I could certainly call that 12, but I want to just be really explicit. So when I do my substitution, step 4, I end up with 6 times 2 u to the 5th du. And there is the point to u substitution. That I took a problem that was really quite complicated looking, did my u substitution, and came up with something that's really quite easy. Step 5, still unnecessary. We'll eventually get to it. Have one variable. So 6 integrating, that's going to be 12. Increase the exponent by 1. Multiply by the reciprocal a new exponent. And then 7, that's going to be 2. And then u was tangent of 1/2 x. So I have 2 times tangent to the 6th, 1/2 x plus c. And since I have the room, we're almost out of time on the video, so I'll start the next video by checking this because I do have the room. But there's my answer, and on the next video we will check it and make sure it's correct.